Good day everyone. My name is Nurzairi Natasha binti Muhammad Najib and my metric number is E25A3657 and I'm from Group 2. Today, I will begin our group presentation on landslide mechanics, the physics behind slope failures, one of the most critical real-world applications of physics in earth science. Landslides are one of the most dangerous and frequent natural disasters in countries with mountainous terrain and heavy tropical rainfall. Malaysia, for example, experiences a high number of landslide incidents every year, especially during monsoon season. Landslide may seem like a sudden event, but in reality, they happen due to a gradual weakening of the slope, involving clear physics, principles such as forces, frictions, and energy transfer. A landslide occurs when the downward gravitational force acting on soil or rock becomes stronger than the resisting forces that hold it in place. These failures are often triggered by heavy rainfall, earthquakes, or human activities such as deforestation and construction on steep slopes. However, several real-world factors can disturb this balance. First, heavy rainfall, the main that triggers in Malaysia, increases water infiltration into the soil. Second, human activities such as slope cutting, constructions, and deforestation that weaken the slope stream. Last, natural processes, including weathering or earthquakes, reduce soil stability. When rainwater seeps into the ground, it increases the pore water pressure, which reduces the friction between soil particles, making the slope unstable. By studying the mechanics of landslide, scientists and engineers can predict potential slope failures and design systems to prevent them. With that, I will now pass to the next presenter, Harizan, who will explain about the physics concept and the methodology used in our analysis.
Thank you, Zaire. And Assalamualaikum and good morning everyone. My name is Muhammad Harizan Artis bin Muhammad Mushafi'i. My matrix number is E25A4032. And today I will explain the physics concepts and methodology behind landslide mechanics. So, landslide can be explained using Newtonian mechanics and energy principle. On the slope, two main forces act on the soil. The first is the driving force, which is the component of gravity pulling the soil downward. And the second is the resisting force, which includes friction and cohesion between soil particles. A landslide happens when the driving force becomes greater than the resisting force. In a dry slope, the stability mainly depends on the weight of the soil, the slope angle, the cohesion between soil particles, and the internal friction angle. The driving force increases as the slope becomes steeper, while the resisting force depends on how tightly the soil particles hold together and resist movement. The energy transformation involved includes gravitational potential energy converting into kinetic energy as the soil mass moves downhill. Without the influence of water, this process is controlled mainly by the balance between these gravitational and frictional forces. To modeling this process, scientists use physics-based slope stability simulation that analyze soil strength, slope angle, and soil weight. The factor of safety is used to measure slope stability, calculated using the factor of safety is equals to the resistance forces divided by the driving forces. So, before using the factor of safety equation, we have to calculate the resisting forces and the driving forces first. So, the resisting forces is equal to mu mg cos theta plus cohesion times length, and the driving forces is equals to md sin theta. So, let's take the example answer, which is the resisting forces is 191.42 and the driving forces is equal to 41.46. So, we can insert the answer in factor of safety equation. The resisting force divided by the driving force, the answer is 4.62. So, this answer shows that the stability is good. With that, I will pass this present to the last presenter, Haikal, who will explain about implication and findings.
Thank you, Harizan. Hello everyone, my name is Muhammad Haikal Bermazuki and my matrix number is E25A3615. And I will continue with the findings, implications and conclusion of our study. According to the study by Zhang and Koch, the physics-based model they developed was able to accurately identify areas that were most vulnerable to rainfall and landslides. The model uses physical parameters such as soil strength, slope angle, and water pressure, combined with the real rainfall data to predict when and where a landslide may occur. What makes this approach effective is that it doesn't rely on past disaster records alone. Instead, it uses the laws of physics to calculate whether a slope will remain stable or fail under certain conditions. This means that scientists can forecast future landslides even in areas that have never experienced one before. For example, in the case study discussed in the paper, areas with steep slopes and high rainfall show a much lower factor of safety, indicating that those slopes were near the point of failure. As rainfall continued, the pore water pressure increased, reducing the friction between soil particles and leading to slope instability. These findings have major real-world importance. First, in engineering, the model helps design safer infrastructure, such as retaining walls, slope drainage systems, and erosion control structures. Engineers can use the calculated factor of safety to determine how much reinforcement is needed to keep a slope stable. Second, in environmental management, authorities can use this model for land use planning, identifying which areas are safe for development and which should be preserved as buffer zone. Third, in disaster prevention, this approach forms the foundation of early warning systems. Using sensors to monitor soil movement, for pressure and rainfall, alerts can be sent to residents before a landslide happens. In countries like Japan and Italy, this warning system have already helped save lives by providing early evacuation notices. Malaysia is also adopting similar system in high-risk areas such as Cameron Highlands and Bukit Bangsa. Despite these advances, physics-based models still face a few challenges. They require accurate field measurements of soil properties and weather data, and errors in data collection and can reduce the model's reliability. In addition, environmental change, deforestation, urban development, and climate change can alter slope conditions very quickly, so models need constant update. For future improvement, researchers recommend integrating GIS mapping, remote sensing, and machine learning with these physics-based models to improve prediction accuracy. In conclusion, the study by Zhang clearly shows how fundamental physics concepts, forces, motion, and energy transfer can be applied to solve real environmental challenges. By combining scientific knowledge with technology and community awareness, we can significantly reduce landslide risk and protect both people and the environment. That's all from me. Thank you for listening to our presentation.